Hi, everyone. Thank you so much for the opportunity to be speaking here today to the organizers. And thank you, everyone, for joining my presentation as well. So my talk is Suspension, the Magic Behind Composability, or the Kyo Monad. And we are going to see lots of Scala code as well, but I try to structure the talk in a way that other people from other languages can also follow. Just a little bit about me. I'm a principal engineer at Nubank. I'm working with the core banking systems there. But today I'm not going to talk about my work, actually. It's actually my unpaid work as open source developer. So open source is really a passion for me in terms of building things to explore innovations. So that's what I'm presenting today. That is the Kyo project. I just moved back to Brazil. I'm actually from Brazil. I was living in the US for over a decade, so I just moved back to work at Nubank there. And the last point is actually more of a disclaimer, because I see myself as an engineer, right? So I'm not really a mathematician, not really academia. So it is a mix of academia and industry. So just a heads up in terms of what to expect in terms of my work. So just first to introduce the project, just an overview of what it is. So what is Kyo? So it's a monadic effect system that is based on algebraic effects. So there's some confusion sometimes that people think that direct syntax is necessary for algebraic effects, but that's not really the case. And Kyo provides algebraic effects within a monadic execution. It leverages Scala 3 advanced type system to provide a seamless effect tracking. So it doesn't require, for example, row types or new kinds of type level features to express effect tracking. It also properly suspends side effects, so it provides multi-shot continuations as well. There are some confusion sometimes. People refer to Kyo as a direct algebraic effect system, but it's not really, it's monadic. But we do have a separate module that is for direct syntax as a dialect. It is essentially a CPS transform from direct code to the monadic execution. We also have another dialect that is the combinators module that is more advanced patterns that you see in similar libraries, but as a separate dialect. And this is a real-world engineering project, so it's not experimental. I think I never said that project was experimental, but I see people reference to it as experimental. Maybe at earlier phases it would make sense, but now it's really a functioning library that's not experimental anymore. We've been working on the library for about 3 years. The first year was actually in private, myself working, and the last 2 years with a community of developers. We've been extending and evolving the library very quickly, so we had 22 releases so far. And if you see the release notes, there's each release is really a big package with major changes, major new features. So it's a really quick pace of evolution. We have an active core developers team as well, so a few people that are always contributing and reviewing, merging PRs. And we already have a comprehensive set of primitives, so you can basically do the things that you can do with other effect systems, but with Kyo. I don't know why it did that. Okay. And we are now close to the RC cycle. So we've been breaking our APIs a lot, to iterate and have something that's very intuitive, but we are now reaching a phase where we are going to be focusing on stability to make sure that people can adopt without having too many breaks. So let's go into the main topic of the talk, that is suspension and how it's important for composability. So let's take an example here, like a compiler pipeline. So for example, you have to read some code, and then you have to parse some code, and then type check, optimize, and generate the final code gen. And then down there, I have a Kyo computation. I'm going to make the methods return Kyo computations as well later. But just to start, Kyo has this approach where the map and flat map are the same, and it's essentially the monadic binds. So it's a simplification for people to introduce, start using the library without having to distinguish between map and flat map. But I'm going to cover that better later. And then when we have this kind of pipeline, if you have to make bigger changes in terms of the execution flow, it can be really challenging, right? So for example, let's say that instead of reading files from the file system, we need to start streaming sources to read and compile those sources. So imagine all the changes that you might have to make to an existing compiler pipeline in order to be able to stream things. It might be a big change, right? What if you want to handle ambiguous parsing, right? So you have some possible parsings, and you can disambiguate during type check, for example. How can we do that? Like, it would be a major change, right, in order to do this kind of flow. How about if we need to customize the type checking for a new feature, right? So injecting some new behavior during the type check in order to provide some new feature, for example. What if we want to explore multiple possible optimizations? Imagine like running things in parallel to explore the optimization space faster and providing better optimizations. Or what if we want to batch all code generation in order to have better efficiency, right? So for example, you parse, compile, type check, optimize multiple files, and then you batch that in order to generate the final code. So if you think of how these changes could be like really challenging to implement, because you would have basically to change fundamentally how the computation, how the code is structured. And Kyo provides a better way of doing that. The monadic type in Kyo, we call the pending type. And it's essentially the monadic interface, and it has effect tracking. So this is the signature of the type. So it's essentially, we use this lesser than sign as a way of having a more lightweight syntax for expressing computations. The first type parameter is the type that the computation is going to be providing at the end. So at the end, when all effects are handled. And the second type parameter is the pending set of effects. Okay, so are the effects that are pending to be handled, and we can have suspensions of those effects that need to be handled. And for example, we can have an integer pending I/O, right? So this means that the computation requires handling I/O in order to produce an integer, okay? And here we are using the infix notation for the type, but it's actually the same thing as this, okay? So these are both the same thing, it's just like syntax sugar from Scala. The other example here is, for example, we can have, sorry, I have a typo here, it should be string pending I/O and choice. And the pending set is actually represented as a type intersection. Okay, so we don't need row types. Scala's intersection types is really enough to represent the pending effect set. And if we have, for example, a computation that has no pending effects, then we represent that as an any. Okay, so any is essentially a pending effect set. So if we need to introduce those behaviors, it's actually relatively simple if you are using Kyo. For example, you can stream sources using poll. Poll is going to suspend, to wait for a new item, and then you can stream multiple items for the execution. Or you can use choice to do non-determinism and do ambiguous parsing, for example. Or you can use environments to introduce some strategy to change the behavior of the type checker. Or you can use async to run and evaluate multiple optimizations, possible optimizations in parallel. Or you can use batch, and that's a really good one because it's a kind of thing that's really hard to do if you don't have an effect. So that is, you can basically batch multiple generations, multiple computations, multiple compilations to be able to generate everything at the code gen phase in a batch mode with a better performance, for example. So it's really powerful. If you see how the behavior that these effects are introducing, it's something that really fundamentally alters how the computation executes. And there might be like some confusion because now we are getting capabilities in Scala, etc. And are we just really tracking effects here? It's not really just that. It's suspending and allowing interpretation of those effects. So let's go to an example. I'm going to show how the suspension in Kyo works from different angles to make it easier for everyone to follow. So the first one here, I'm going to show an example where I have a choice evaluation, a choice suspension during the parsing, and then another choice suspension during the type check. So, for example, here we are going to be executing the parsing. Eventually, we get to a point that there is a choice.eval that is a suspension saying, I want to branch the execution of this computation for rule 1 and rule 2. And then during the type check, maybe I have another choice suspension saying, I want to try the regular type check or a new experimental type check. And this is really interesting because we are still representing the computation as a linear execution. You don't have like really branching when you are declaring the computation itself, but the execution is going to introduce that branching for you. And within the kernel, what's going to happen, essentially when you get to the parse method, you're going to get to the choice.eval rule1 and rule2, and then what we are going to save there is the suspension, the inputs of the suspension, and the rest of the computation is going to be the continuation. Okay, so suspending at the parse effect, and then we are going to be building a continuation that has the type check phase, the optimize phase, the code gen phase. Okay. And then in the choice handler, eventually you can handle this effect choice, and it's going to basically evaluate the two rules that were requested for the same continuation. So you are essentially branching the computation to evaluate multiple possible outcomes. And that is an iterative process, right? So we are going later to be evaluating rule 1, evaluating rule 2, and then we might have a new suspension in the type check phase that is going to evaluate a possible regular type check or an experimental type check. And at that point, we are going to have the same process. Suspension, building the continuation with the optimize and code gen phase, and then the handler is able to evaluate those in parallel. Not parallel necessarily, but like two possible outcomes of the computation. So that's an initial view of suspension I'm going to show from other angles as well. So continuations are first-class values in Kyo. You can resume with arbitrary values, so you can take the inputs of the suspension, you can transform, you can inject something from the environment, so it's really powerful in that way. Handlers can resume computation 0, 1, or n times, so it's essentially multi-shot continuations, because the continuation is just like a monad instance of a suspended computation. And this really unlocks a new level of expressivity, because if you think of how you're altering the control flow of the execution of the application, you normally have to have like new syntax in the language. You have to have new language features to express that. But with algebraic effects, you can actually express that without new syntax, without new language features. Now I'm going to show from another perspective that is actual Scala code. And I apologize, like there's people from other languages, so I tried to structure it in a way that's easier to follow. But if you have questions later as well, feel free to reach out. So let's see how we do the suspension of the parse, and then we call choice.eval, right? Trying to evaluate the rule 1, rule 2 for parsing. And the mentality of how Kyo's core works is really, what is the simplest thing that we can do? Okay, so for example, how can we express a suspension? And it's essentially what information we have. That is, the effect that was suspended, the input of the suspension, and a continuation. Okay? And then, in this case, we are going to have a suspend of choice that has the inputs rule 1 and rule 2, and then a continuation. Okay? And then we have the next transformation. What do we do with that transformation, right? We just append to the continuation. And then we have a new transformation. Can we just accumulating? Yes, that's what Kyo does. Once you suspend, it's going to keep accumulating transformations until it reaches the handler that is matching that suspension. And then it's just really that it's like, that's how we build the continuation in Kyo. So, okay, that's another way of looking at suspensions. Let's now see how we can express effects, because it's not only about having the continuation, having handlers, it's really how can we express effects in a way that's type safe, and you can express a wide range of possible effects. So let's look at the choice eval method. So that's going to be introducing a suspension for choice, and it goes from a sequence of values, A, of type A, to a computation that has A pending choice. Okay, so it goes from a sequence to a single value. Okay, and that's something that's not so easy to express. So we had like many iterations of the Kyo's kernel to represent this kind of effect, and we landed on a implementation that allows us to have, for example, a choice.eval that is of integers, but also have a choice of eval of strings, for example, and that being fully type safe. The main abstraction that we use for that is the arrow effect. And this is not really like a precise academic definition of the arrow effect, but it's essentially two type lambdas. One defines the inputs of the suspension, so it's like an abstract arrow. And the second type lambda defines the output of that suspension, of that effect. For example, we can have the choice effect, representing going from a sequence of A to A, right? So for example, here we have a type lambda showing that for the input and the output. And Scala has a really nice syntax, so we can actually just do sequence for the first type parameter, and the second one, we have two aliases, ID, that is just like the identity type, and the const type as well is another one that we use. For example, we can have the environment effect. So environment allows you to ask for a value from the outer scope, from a handler, and it's interesting because it shows that effects can also be parameterized, right? So you're requesting a type environment of type V. And the inputs of the env effect is actually a unit because like you're not really passing anything, you're just requesting a value of type V, but the return is a const of type V. Another example is the Paul effect, that is the streaming effect, where you essentially have the inputs as a unit, and the output is actually an option of V, indicating if you have a new value to continue streaming, or if the stream has ended, so the computation should not request more values. And then we have the emit, that is actually the opposite of Paul. It allows a computation to emit values during execution, so a handler can gather those values, right? So the inputs are V, and the outputs as a unit. So that's like how we can express effects, and that allows us to express them in a fully type-safe way. Now I'm going to build the kernel. That's the part of the talk that has more Scala code. So please bear with me. I'm going to show that from other perspectives as well later, if it's difficult to follow. So just recapping, so we have the arrow effect with two type lambdas for the inputs and outputs. And then we have the expression of a pending computation that is going to produce A and has a set of pending effects. And we have only two possible states of a Kyo computation. One is it's a computation that finished. There are no pending effects anymore. We have a pure A. Okay, that's one case. And the other case is the one that we saw before. It's a suspension. And sorry that we have like all the type parameters. If you're not used to Scala, it might be difficult, but maybe focus on the structure of the case class, right? So we represent effects in Kyo as a pure type level construct. So we don't really instantiate an effect during the execution. And for that, we use type tags to represent effects, essentially. And then we have the input of the suspension, and then we have the continuation that's going to take the output of the suspension and resume the computation until all transformations are finished. Okay. How can we implement transformation of these two possible states? So this is the monadic bind as an extension method. So it's A pending S. And it's going to be taking a transformation function, a bind that is taking A, a pure A, an actual value A, and then producing a computation B pending S2. And this is a really important property of the monadic binds in Kyo. That is, once you bundle those two possible computations with S and S2, you're going to be producing a B pending S and S2, right? So you're composing those effects and tracking them to make sure that they are later handled. And we have two possible cases for the bind, right? So pure, we actually just do call the function, right? So some might be thinking here, oh, how about stack safety and etc. That's something that we do encode stack safety through safe points, but I'm not going to be able to cover that today. But in general, we can actually go through execution without having to suspend computation on every transformation, you to an interpreter, and etc., because that's really expensive, right? So you can get really much better performance this way. And then we have the suspend case that is just like continue accumulating the transformation. So really simple mental model of how the algebraic effect encoding works. Now, it's probably the most complex code in the presentation, so, but I think it's not too much code. I think it's possible to follow. That is the handle methods. So when we are handling an effect, we take the tag of the effect that we want to handle, right? And then we take a computation here that is of type A, pending the effect E to be handled, and an arbitrary set of possible other effects. Okay? And then if you see the return type in line 7, it's going to be A pending S. So we are handling the E effect. We take it out of the pending set. Makes sense, right? And then this is a bit more difficult to read, but it's essentially the handling function is going to take the input of the suspension, the continuation, and then return a new computation. Okay? And handlers in Kyo, they are required to eventually reduce the computation because otherwise you'll never finish. But you can actually continue suspending with the same effect as well, because you can have patterns of expansion and contraction in effect suspensions as well. And the implementation of handling is actually three possible cases that we have to handle. So the first one is the pure case. And it's very simple because if it's pure, there are no suspensions, we can actually discard the handler. We can just ignore the handler at that point. And if it's a suspension, then there are two possible cases. One is it's a suspension of the effect that's being handled, or if it's a suspension of another effect. What we do in those two cases, right? So if it's a pure case, like I mentioned, we just return pure as well. And here, maybe people that are used to algebraic effect solutions, normally you have a pure handler and an effectful handler. In Kyo, we have this theme of trying to simplify as much as possible. So we actually don't have the pure version of the handler, just like the effectful one. And we can handle the behavior of the pure version in a different way that I'm going to show later. For the case where the effect is being handled, we need to call the handling function, right? So we are going to pass the inputs of the suspension, we are going to pass the continuation, and then we have to recurse the handling. Because once we resume that specific suspension, the continuation might have other suspensions of the same effect. So the handler needs to continue there. We can't just discard the handler, right? And the last case is, I think, the most interesting in Kyo, that is what we do when we are handling an effect that is not the one that is suspended at the moment. We can't really discard that handler because there might be new suspensions of it after that initial suspension that we are handling now. And what Kyo does is this rotation of the handler. So essentially, it's going to suspend again with the same tag 2, the same other effect, the same input, but then it's going to move the handler to the continuation. So when the initial effect that's suspended resumes, we are going to continue, evaluate the continuation, and then continue handling the same effect, so we don't miss any possible suspensions. Cool, so that's essentially all of the Kyo's kernel. It's not very much. We have two other important details. It's more about usability. That is essentially, how can we evaluate a computation, right? So we get to a point that we handled all effects, and the pending set is any, it's empty. How can we get from A pending any to A? And then we have the eval method that is going to be essentially saying, it's proved by the compiler that it's a pure computation at this point because there are no tracked effects anymore, right? So, and if you look at, for example, Kyo's repository and issues, we never had the bug case, for example, reported because the type system is able to properly handle those effects, unless you do like as instance of, like you do unsafe typecast, then you're on your own. But it's really a proof in terms of like the type system proving that there are no pending effects anymore. We also use automatic lifting for mostly usability, and also because when we do the pure version of Kyo in the actual implementation is actually unboxed. We don't have an object boxing it. So essentially for better performance, right? But the automatic lifting is essentially using implicit conversion from when the compiler sees that a Kyo computation is required and you have just a plain pure value, it's going to lift that into a Kyo computation that is A pending any, essentially. So, for example, you can refer to a plain integer value as int pending any, and that's going to be satisfied by the compiler. And you can also have this monadic binds, the map methods, taking a function that's returns just like a pure value, right? So if I'm calling to a string here, it's actually going to be just a string. It's not going to be a Kyo computation, but the compiler is going to introduce then this implicit conversion in order to make it so we can use map and fatmap as the same methods. Cool, so just a couple of example effects. I'm not going to be able to go through many effects, and also it's too much code, so I don't want to overwhelm everyone. So this is the environments effect. Also here I'm putting the variance annotations as well. In the actual implementation also we have that, because then you can track multiple environment values as well. And the environments effect so the actual kernel is free, right? So you can do suspension, handlers can come from anywhere, but we try to package effects for the users, right? Because building effects, handling continuation is something that's a higher level of abstraction. So we try to provide the building blocks, the effects that people can use in order to build systems without having to handle effects manually. So the environment effects are going to have get that's going to be suspending, requesting that value from the environments. So it's going to be a V pending environments of V that needs to be provided, handled later. And the handling methods, we have this convention of being the run methods. The signature here is a bit more complicated, but essentially injecting the V type into a computation that has the NV pending effects. Okay, so satisfying that effect on the computation. And we call the handle method that we saw before, passing the tag of the effect, the computation to be handled that has the NV pending. And the handling function is going to take the inputs that was used to suspend, that is what was units, right? Because we use const units for env. And it's going to have a continuation that takes V and produces runs the continuation until the points of suspension. So the continuation here is guaranteed to be from the exact points where there was a suspension to the points where you're handling the effect. So it's a really strong guarantee in terms of behavior. And then we can just pass that environment to inject that value into the computation. This is another one that is the abort effect. I wanted to show you because it shows that we don't really need the version with the pure handling in the handler itself. Because here we are going from a computation of A pending abort E and S to an either of E and A pending S, right? So how can we make this transformation of the actual type of the computation? We just need to append a computation at the end of the handling function, the computation being handled. Okay, so we just add the writes. If it reaches the end, it's essentially meaning that there are no abort suspensions, so we are actually with a successful write value. But if it's actually suspending with a failure, it's going to be suspending with an input, the continuation, and the input is going to be the failure. And we just short circuit not calling the continuation, right? Because we are failing the execution and pausing, halting at that point. Cool. So this part here, I think it's more sensitive and in terms of being not as formal, but I wish people are able to understand where we are coming from. But essentially, I believe Kyo is probably the first algebraic effect library that has laws for algebraic effect handling. Normally you have solutions that are more unconstrained, right? So you have free interpretation of effect handling, and it's really hard to guarantee and have a good mental model of how things are going to execute without laws, right? Because then you don't know how one handler can impact the other, so you have proper isolation of the effect handling. And it's another way of looking at how Kyo does suspension as well. So first we have Kyo satisfies the monadic laws, that is left identity, right identity, and associativity. It's really interesting because, for example, left identity, it's actually, the actual implementation is that, right? So it's by construction satisfying that. And right identity, associativity, also, they are enforced by construction. Normally other libraries you have, for example, creating this AST to be interpreted, and then these laws are guaranteed by the interpreter that has that behavior. In Kyo, that's actually by construction, those laws. And then we have the new laws for effect handling. So the first one is pure handling. So if you are handling a computation that's a pure value, it's done, there are no effect suspensions anymore, that's just the pure computation. We discard the handler. If it's the case where we are handling one effect, but the suspension is also suspended with the same effect, then we have the effect handling logic. That is, we are going to have the F handling function, and we are going to apply that to the input and the continuation. All right, so, and we need to recurse the handling again because the continuation, once it resumes, it might have other suspensions of the same effect. So we have to continue with that handler installed. And the last one is, I think it's probably the secret sauce, I would say, in terms of how Kyo works. That is the handler rotation. That is, when you have the case where the suspension is not the one that you are handling, what do you do with the handler, right? Because essentially, you can't just discard the handler. You have to make sure that that handler is going to be handling possible suspensions in the continuation. And what we do is just rotate the handler. We pass the handler to the continuation, and we continue with the same suspension, the same tag, the same input, but we put the handler to handle potential suspensions in the continuation. So, and then you probably might be thinking, where is the proof, right? And I'm sorry, like we tried with Lean, for example, but Lean is difficult to express the effect tracking in Kyo. Because it doesn't have like intersection types like Scala has, for example, right? So we couldn't really make produce a proof. But we have like kind of like approximate proof, and I'm sorry for this to say this in a more academic conference, but we do have all the common effects that you see in normal algebraic effect solutions. So I created this visualization that is, you can just click on each of the effects, and then you can actually see the source codes, and it has documentation, etc., to follow if you want to have a look. And you have to do some mapping because we don't use the names from, for example, category theory or more formal names. We try to use names that not scare people. So the idea is to have people like that are not like functional programming people to be onboarded in functional programming, right? And I'm going to mention briefly about other things that are necessary to make this an actual reality for usage. We introduce stack safety by having safe points before each transformation, so you can actually, the library is tracking the depth of execution within the stack trace, and then that's going to be introducing suspensions to unfold the stack when necessary and ensure stack safety. We use unboxed representation for playing pure values. That's something that avoids a lot of allocations in the execution and makes monadic execution being much more efficient. We also use inlining as a way of computation staging. So if you have, for example, pure value computation that is a pure value map, that's not going to be allocating anything unless you reach like the stack depth and you have a suspension, but it's in general like not allocating. And that really puts in check some of the assumptions you have about monadic execution not having the ideal performance. I think that's an interesting exploration for example, a new talk. We also have two kinds of effects in the kernel, that is the context effect and arrow effect, and that's mostly for performance. The context effects, but also for forking with computation, so with effects. So we can actually, in Kyo, we support forking with pending effects that it doesn't seem to be a common feature. I couldn't find matches in other libraries of this kind of pattern. And we also have this mechanism called isolates that allow you to more granularity into how to handle effects together. For example, when you're forking with a state monad that we call var in Kyo, you can have like more granular behavior to ensure that you can do that, forking with effects, but in a principled way without having issues with that. So just to conclude, first I want to say a big thank you to all contributors. Especially, I think it's been really great to like leverage the power of like open source collaboration to build Kyo. And especially I wanted to say thank you to Adam and John. They've been contributing since like a long time now and like steady contributions. So it's been really great to collaborate with everyone. Feedback is appreciated, so if you want to criticize or anything that's negative or positive, like it's everything really interesting for us because we are in a phase that we are going into stabilization, right? So having feedback from people is something that's really valuable to ensure that we have something that's useful and people are going to be able to have a good experience with the library. And we would love to collaborate on a formal proof. I might need more help to do something like that, but it's something that we would be very eager to collaborate on. And please keep an eye out for the 1.0 RC1. We are probably going to have a few releases for a few months to make sure the APIs are stable, everything is stable, and then make the final 1.0 release. So yeah, that's it. Thank you.
Thank you very much. Any question?
How does it affect performance?
In what sense?
Well, generally, when you introduce more elements into your stack, performance may suffer. Have you done like benchmarks versus when you use this versus when you don't? Is my first question. And my second question would be, if I want to try it out and play with it, like what would be a good use case that you would advise?
Okay. So regarding performance, you are right. Like if you have multiple handlers, then you have to keep suspending those handlers, and that can have some overheads. But there is an important offset of that performance overhead. That is when you have normally most computations in real applications have many more transformations than effect suspensions, right? And the transformations in Kyo are really cheap. So they are not even going to suspend if the stack depth is not reached, the limit, and it's not going to even allocate anything. So you have a big offset in terms of performance overhead in the pure transformation case. And we have like lots of optimization. So the library is really focused on performance. So in Scala 3, we have inlining, we have opaque types as well. So for example, common representations like in Scala that are boxed. Like for example, if you have an option, you have a boxing object that's going to be allocating. We have another encoding is the opaque types and union types that is unboxed. So you don't have like the wrapper object. So there are many techniques to optimize the library, and it's a major focus in terms of execution, having something that's really with good performance. And we are always optimizing the library. That's a major focus. And then regarding possible usage, I would say, for example, if you have an existing system where you are using Scala, you could adopt Kyo like in isolation. If you see the effects, for example, we have different modules, right? So the Kyo prelude is just like pure effects. You don't even have I/O there. So you could like compose a computation that's pure, evaluates in place without breaking gravitational transparency, and then like you can integrate with other parts of the system using other libraries, for example. That's a really good use case. And the general use case is really this focus on performance, something that requires more, better performance, and especially this expressivity of effects, right? Where you can customize the behavior, customize the execution in a way that's more powerful than just like regular execution. Make sense? Thank you.
All questions?
Hi, thanks for the talk, Flavio. I have a question. Are you aware of anybody trying this in production, to use Kyo in production, and also if you would already encourage it, maybe?
We've been not encouraging usage in production, so because we've been breaking the APIs a lot. So if you adopt a library until now, like it'd be a nightmare. Every new release, you have to make like lots of fixes. So that's something that we are not encouraging so far. But that's the main focus for the RC cycle, to have a stable. So we are going to, for example, if there are breaking changes, we are going to try to provide automatic rewrite rules or changes, for example, and make sure that the experience from the RC cycle on is going to be something that you can actually adopt. In terms of production usage, I don't think there is any yet, because it's really something that we've been iterating really fast the past couple of years, 3 years. Yeah. Thank you.
My question is from the point of view of a person that considers choosing Kyo versus Katz effect or Zio. Mm-hmm. Would you have any ideas of an application where Kyo would clearly be the better choice and it would shine, and applications where Katz effect or Zio would be definitely better choice?
So I would say where it shines would be probably performance is a major focus of the library. And if you need more complex behaviors in terms of execution with effects, right? So you can customize execution in a way that's not even possible with Katz effects or Zio in a straightforward way, right? So you can kind of like simulate the same behaviors, for example, with tagless final or MTL, but like the usability is really difficult. Another good use case is because Kyo allows you to express new effects as well as a user, right? And that new effect can be used with the other effects together. So if you have like a new API, like an integration, I don't know, with GPU, we were talking yesterday about it, and you have a few operations that you want to express, you can create a new effect for that, but then you can also leverage all other effects with that new effects. So you can have parallelism, you can have non-determinism, you have like everything together with your new effect. And I think for the other libraries, I would say they are more mature, right? They are used in production, they are for a long time. So I would say it makes sense, like if you have a production system today, it makes more sense to use Zio or Katz effect, for example, right? But the goal is to have the same scope, the same kind of solution as Zio or Katz effects have in terms of functionality.
Another question? A question myself. You chose to use intersection types for the pending suspensions. Okay. I don't think that it is a better alternative. But did you think about tuples?
It wouldn't work well because with the intersection type, you can have, for example, because it also has variance. So you have a computation with a pending I/O. You can pass it to a signature that requires a computation pending I/O and environments of something. So you have also the variance playing an important role in effect tracking. So you can widen the pending effect set by just like passing things, and the compiler guarantees that's safe, right? So there are other behaviors that are encoded through the type intersection.
Okay.
Makes sense? A question over there.
Do you have interoperability with other effect systems?
Sorry, integration?
Interoperability with other effect systems.
Yes, we do. We have two modules, one for Zio and another for Katz effects, to integrate with them. It's integrating through fibers, so it's not really like a pure way of integrating. We could have other ways of integrating but we don't have that yet. But it's really useful. If you have your Zio application, you can just like run some computation, transform that into the Zio, from a Zio computation, transform into a Kyo computation, so you have like bidirectional transformations between the two libraries. Other questions?
Some more questions? One big one? Okay.
Okay, thank you for the nice talk. I have a question about the intersection types. So they are very good for modeling, but the type inferencer sometimes is not very good at them, at inferring them. Is that your experience as well, or how did that work out for Kyo?
That's a good point. Like, for example, removing things from the intersection can be challenging. So we went through multiple iterations to be able to encode that. But I think the final approach, like just declaring the type signature of the methods, the intersection, then removing there from the type signature is really elegant, works well. The other thing that's problematic is you can't really destructure type intersections well. So if you have like a type lambda that you want to destructure to select and remove one item from the type lambda, for example, right? You can't do that, so our macros can't really introspect well. So we had to implement like a macro, for example, to the isolate mechanism to ensure that we are forking with the effects that are supported, because you can't really introspect well with the regular type system. So we had to use a macro for that, for example.
Thank you.
So anything else? Any more questions? Okay, thank you very much, Flavio.
Cool, thank you. Thank you, everyone.